There are two main applications that you can find when it comes to the most basic facts about modular arithmetic. So let me provide it. The first one is basically insights into the integers themselves using this new structure that we constructed on the integers, right? This structure that behaves slightly different from the integers, but still gives us information about them. So let me give you one example, and then we will talk about the second application, which is solving equations and something called Diophantine equations, basically equations with integers, involving integers, and where we're trying to find integer solutions. So for the first application, here's a basic fact that you can prove, you can verify this. I'm not even going to write this as an exercise, but you can do that. So any natural number or any integer, but I don't want to have to write a minus sign. So any integer, any natural number n can be written as n equals the power of 10 to the I times a to the I, right? How would you do this? Well, you can just divide by bigger and bigger powers of 10 to find these coefficients a sub I. This might seem a bit abstract at first glance, but let me tell you that this is actually very, very easy, and it's something that you've been using for a really long time. The common notation, which is called the decimal digits notation, or the decimal numeral system. Decimal positional notation is that you already know that n can be written in this way. So what you typically do is you say n is a k minus 1 all the way up to a1 and a0. Right, so let me give you an example, and you'll see that this is something that I'm very sure you haven't used for the first time. Notation. So for example, the number 256 is actually a combination of three different digits, the number 2, the number 5, and the number 6. But the position of those digits tells you what role they play, right? So this would be, maybe I'm going to change the order of the digits so that it matches our left to right notation, the way we write. It's obviously the same thing. So this is 2 times 100, or 10 to the 2, plus 5 times 10, or 10 to the 1, plus the units, which is 6 times 10 to the 0, or just 1, right? So this is how we typically write numbers in decimal notation. We could have used a different base. We can also write any number in binary form or ternary form. And what I'm about to say will change depending on what numeral system you choose. But I think I think it's fair to say that most humans on Earth use the decimal system for whatever reason. So let's start with that. And if you're curious, then you can think about how these rules would apply if you instead write a number in ternary form, for example. So this is what I want to do. So the theorem is, I want to figure out whether a number is divisible by another number by looking at its digits. If I give you a really large number, say it has 1,000 digits, and I'm asking you, do you think this number is even or odd? You probably know that you don't really have to look at all the digits to decide this question. So for any, obviously this works for integers, but like I said, I don't want to write the minus sign everywhere. So for any natural number n, okay, so let's say that n, we already found its digits, so let's say that it can be written as ai 10 to the I. N is divisible by, and then we're going to add a bunch of stuff here. So the first criterion is divisible by 2, or is an even number, if and only if the last digit, so the unit a0 is divisible by 2. 2 divides a0. So if you have a really big number and you need to see if it is even or odd, all you have to do is look at the last digit, and if it's even, then the whole number is even. Now, I'm sure you know this, but why would this be true? How do you prove that this is true? Maybe let's write down the proofs here in the middle of the theorem, just so that it's a bit easier to keep track and it motivates the future facts as well. So let's try seeing why this is true. So you take this natural number n, and to know if something is even or odd, the way I defined it in the lecture, is that you reduce it mod 2, right? But recall that n is equal to this whole thing, right? So maybe let me just copy paste this. So this, which is the decimal representation that we found for our number n, this is the thing we're actually reducing mod 2, right? And you know that congruence classes form a ring. That means they behave nicely with addition and multiplication. This is basically the fact that these operations are well defined for the class, the equivalence classes of congruences. Another way of saying what I just put into words is that you can basically, to reduce this whole expression, all you have to do is reduce each of its components individually, because this is a sum and then a product, and these behave nicely, right? So if I manage to reduce the AIs and I manage to reduce the 10 to the I, then I can just add those reductions together and then multiply them and then add them together, right? So what is 10 mod 2? Well, 10 is an even number, and so is 10 to the 2 and 10 to the 3 and 10 to the 4. All powers of 10 bigger than or equal to 10 are even. 10 to the 0, which is 1, is of course odd, so that one does not reduce. What I'm saying is what you should get here, if I expand, maybe let's expand this out in this different notation, so that's a bit more familiar for most of you. So this is 10 to the k, a1, 10 to the 1, and a0 times 10 to the 0, I'm not even going to write down because it's 1, right? So now I reduce this mod 2. So what is ak mod 2? Well, no idea, but 10 to the k is 0 mod 2 because it's even. So this will be 0 all the way to, maybe let's include the coefficients just so you can see the indexing. So ak times 0 plus a1 times 0 plus a0. And of course, this is equal as an integer just to the number a0 because everything else has a 0 in front of it, right? So this is just a0. And this finishes the proof because n is congruent to a0 mod 2. So either they are both 0 mod 2, meaning an even number, or they are both odd. Therefore, n is 0 or even if and only if, maybe I should write it in words, if and only if a0 is 0 mod 2. because they are equal, mod 2, right? So to know if a number is divisible by 2, you only have to check the last digit. Let's look at something a little more elaborate. When is a number divisible by 3? Well, maybe you know this rule, maybe you don't, but let's pretend that we haven't figured this out yet. So why don't I start by writing the proof before I come to the fact? And this is something that you do when you're discovering mathematics, right? Sometimes you have to start writing a proof of something that you don't even know what the statement is of it. This is how you would figure this out. So let's do this for 3, and maybe you can do some other criterion as an exercise. These all follow the same basic rule. Okay, so let's do the same trick. N is going to be 10 to the k, sorry, a k times 10 to the k plus a1 times 10 to the 1 plus a0. And this time we reduce it mod 3 to figure out if a number is divisible or not by 3, right? Now 10 is 1 mod 3 because it is 9 plus 1, and 9 is of course divisible by 3. So this should just be ak times 1 plus all these powers of 10 are 1 mod 3, right? There is a property, one of the first properties I wrote down about congruences is that if two numbers are congruent, then any power of those are congruent, right? So 10 is congruent to 1 mod 3, meaning 10 to the k is congruent to 1 to the k, which is just 1 mod 3, right? So all powers of 10 bigger than or equal to 10 are just 1 mod 3. And let's do this all the way to the end. A0, right? More succinct way of writing this is that this is just the addition of these. All the 10 disappear. Am I starting the index incorrect? Yeah, I did. Okay, I'm not even going to write the conclusion because the conclusion is, of course, that something is divisible by 3 if and only if you add up all the digits, you only get something divisible by 3. This is, of course, very quick because adding the digits, even for a large number like a 20-digit number, is a very easy computation, and you're usually going to get, you're always going to get a much smaller number when you do this. And you can do this over and over again, right? If you start with 1,000,000 digits and you add them up and you get something like, I don't know, like 1,000 digits, that's still too large, so you add up the digits again. And if you do this, eventually you will get down to just one digit, and that digit will be either 3, 6, or 9 in case it's divisible by 3 or 0, or something else. Right, so this is how you could easily figure out if a number is divisible by 3 or not just by looking at its digits. So this is a very, very neat trick, and I think there's an additional problem in the problem set that uses something like this. Okay, so I have a question in the chat that is very relevant. Why do we know that 10 to the k is 1 if we don't know k? Okay, that's a good question. And let me address this. So let's do this before we write this down. So notice, let's add some more details, right? So notice that 10, which is just 9, or 3 times 3 if you want, if you divide it plus 1, this is congruent to 1 mod 3, right? But this is something that I previously said, right? If two numbers are congruent for any k, bigger or equal to 1, 10 to the k is 1 to the k, which is 1. Okay, mod 3, right? And this is a property, one of the first theorems, basic properties about congruences. You can check that we did this. And I think the proof was left as an exercise, but it is immediate using induction on k, right? So this is the part that works for k equal greater equal to 1, and the part where k equals 0, well, that one doesn't matter because it is already 1, right? 10 to the 0 is already equal to 1, so in particular, it's congruent, mod 3. Yes, yes, thank you. So someone in the in the chat also gave, I think, the same idea. Yes, you're welcome. Okay, now let's maybe do a few more. I don't really want to do all of them in this level of detail because you can see it's the same trick every time. Actually, maybe here we can already start abstracting, right? So when do you know if a number is divisible by 4 or not? So what do you think? Numbers divisible by 4. This time we might need a little bit more, right? So proof. Maybe let's just write the first part. So 10 10 mod 4 is 2. So that is problematic because, well, if I exponentiate this to k, I won't get something that useful, right? 2 to the k is just powers of 2. That doesn't simplify, at least not apparently. In general, of course it simplifies mod 4. So this one is not the one I care about. But if you go a little higher, 100 is of course divisible by 4 because it is 25 times 4, right? So let's write this just to be as clear as possible. Times 4. 4 is of course 0 mod 4, so therefore 25 times 4 or times 0 must also be 0. So 100 is divisible by 4. And that means that 10 to the k must be 0 for all k bigger or equal to 2, right? Because 0 to the kth power is, of course, still 0. Okay, so this is easy, right? Because then we just have the same thing as always. This is ai 10i reduced mod 4. What I get would be all the powers of 10 bigger than 1 are eliminated because they're just 0. All I'm left with is the last two. The one that had a 10 times a 1 and the one that doesn't have anything, a 0. So this is if the last two digits, or as a number, as a two-digit number, okay, maybe I should just write it the way I've been writing all the others. So all you have to do is look at the last two digits, right? So a1 plus a0, or the number obtained from just the last two digits, is divisible. Is divisible. Okay. 4. 5 is divisible. Sorry, 5 divides n if and only if what? What happens if you reduce this expression mod 5? All the powers of 10, of course, are divisible by 5, so they eliminate except the last one, the last digit, right? But the last digit can only be a number between 0 and 9 inclusive, and the only numbers divisible by 5 are 0, which is divisible by everything, and 5, right? So another way of saying this is that a 0, because it's a digit, has to be either 5, 0, or 5. By the way, I didn't define the word digit, but I'm pretty sure you know what this means. So let me maybe add a few more details at the top here. Can be written as, so of course, where each AI is digit, called a digit, right? So a number between 0 and 9. So there's 10 possibilities, and that's why this is decimal notation. Now, I would encourage you to think about these criteria with a different numeral system like binary or ternary, because of course they change, right? I would be changing the base. So instead of a 10 to the I would have a b to the I. So this is something not a non-trivial thing, right? Okay, I'm not going to prove this one. We can think about the number 6 if you want. That one can be proved either using the same trick that I just did now, or using some facts that I will tell you about in a second. So 6 is number divisible by 6 if and only if it's divisible by 2 and 3. right? Two ways of doing this. You can either do the same trick we just did for all these other numbers, or use the fact that 2 and 3 are coprime, right? We'll talk about this in more detail in a second. People usually skip the number 7 because it's kind of odd. It's not such an easy criterion, so maybe let me do the same. A number is divisible by 8 if and only if what? I want you to tell me what you think this criterion should be. We're almost done. So divisible by 9, 10, and 10 is 1 mod 3 for the same reason that 10 is 9 mod 3. So we get actually the same criterion we had previously for the number 3. So a number is divisible by 9 if and only if adding up its digits gives you something divisible by 9. Exact same argument. 10, this one's easy, right? The number is divisible by 10. 10 is, of course, 0 mod 10. So all powers of 10 get cancelled. So all you have to worry about is the last digit. But the last digit can only be divisible by 10 if it is 0, because all the others don't work. They're smaller than 10, right? And you already know this. You already know that a number is divisible by 10 if its last digit is 0. And of course, this applies to bigger powers of 10 as well. What about 11? 11 is also nice to work with because it is just 1 bigger than 10. So powers of 10 mod 11 are just minus 1 to the k. And those are usually easy to figure out, right? So let me maybe tell you what the criterion is. And this one I suggest you do solve as an exercise. So here you have to alternate. You cannot just add up the digits. Sorry, it's an I. You have to alternate digits. You add them up, which is just as easy as adding them up, right? So I suggest you do this one as an exercise. And this one as an exercise. Like I said, this might be a bit harder than the others because there's 2 ways of doing this. And it might require a little extra step, but it's the same idea. There's nothing that I haven't taught you that you need to solve this. But there's easier ways of doing that, and we will address that in a minute. So what can you tell me about the criterion for 8? When do you know if a number is divisible by 8 or not? So if you reduce 10 powers of 10 mod 8, well, 100 still doesn't cut it, but 1000 is divisible by 8 in all bigger powers of 10. So here, the basic idea is you have to look at the last 3 digits. A2 plus 10 times A1 plus A0. A number is divisible by 8 if and only if the last 3 digits are divisible by 8 as a 3-digit number. So these are most divisibility criteria. You can come up with more. You can come up with how these change for different numeral systems. All these rules, of course, no longer necessarily apply. For example, in binary, a number is divisible by 2, or is an even number if and only if the last digit is 0. So the same rule applies for 10, or for any numeral system, any basis that you pick, it's going to be divisible by that basis if and only if its last digit is 0. Right? So you can generalize this in more than one way. Now, we didn't really explore numeral systems as a subject as a whole, so I'll probably not ask you anything about, ternary or binary, but it's worth knowing because some problems become simpler when you think about them in different numeral systems. Decimal is not always the easiest, right? Okay, so this is the first application, divisibility criteria, so you can easily figure out if a number is divisible by something. Another criteria which is important, which I'm not going to address during the lectures, but it is going to be addressed during the tutorials and in the problem set, is you can prove that certain equations don't have a solution by reducing them mod an adequate number. Because if an equation has a solution, well, then the congruence should also have a solution, right? So if you reduce it mod something and you find a contradiction, that means that the equation doesn't have a solution. So let me just tell you what I said, but in a bit more abstract way of things to come. So this is something that I will not necessarily cover in this lecture. The last subject is quite open, the last chapter, and I want to send out a survey to all of you and ask what you're interested in so that you all benefit as possible, as much as possible from the last chapter. So there's something called Fermat's last theorem. I don't want to write this as a theorem though, so conjecture, maybe fact. And this is called Fermat's last theorem. And it is the fact that this equation doesn't have solutions, doesn't have integer solutions except the trivial ones. Does not have non-trivial meaning non-zero, non-trivial solutions for k greater equals 3. This is perhaps one of the most famous problems in all of mathematics, particularly number theory, and it has a really interesting story of the person or the people, plural, who managed to solve this. It was quite an achievement because it was considered one of the most difficult problems ever, right? It was left open for hundreds of years and it became really famous, and a lot of people attempted it and failed. So it is a very important story. Of course, I will not prove this. I have no idea how you prove this, and we will not cover this in the lecture. Um, yes, exactly. So someone in the chat mentions that Fermat was writing lots of notes on number theory, very, very important advancements and things that we will talk about some of his results. And in these notes, he wrote the comment, as you probably know, I know a perfect proof, but the space is too small for it. And it is very likely, and people are mostly convinced, that he did not have a proof of this, because it is very unlikely that this fact has an elementary proof. So people are pretty sure that he was either wrong or just plain lying. Anyway, so I'm trying to prove that this doesn't have a solution for a certain condition, this equation. So one idea to solve Fermat's last theorem would be to take this number and reduce it mod an adequate prime p, right? For some large prime, some very large prime, but anyway, for large prime. And if we manage to show that these are not congruent, well, then I have solved the problem, right? Because if this had a solution, then I should be able to reduce it mod p and get to the same number. So if I manage to prove that this doesn't work with prime number p, then this would solve Fermat's last theorem. So this is one approach, and this was attempted by someone called Schur in the 1920s, 1930s, I believe. And of course he failed because this is not the way you solve it. But he came up with something which, in my opinion, is just as interesting, which is how do you prove that this doesn't work? Why doesn't this approach work? So sure, think sure attempted this idea, found that Fermat's last theorem. I'm writing it this way because there's something called Fermat's little theorem, which we will cover, and I don't want to cause confusion. So Fermat's last theorem fails in prime characteristic or mod p, and I find this really interesting. This fact, the fact that you cannot solve Fermat's last theorem using modular arithmetic, is interesting enough in of itself, and it is something that we could cover if we dedicate, I think, the last 2 weeks, all the last lectures to this fact, because it is very combinatorial. It is something that we haven't discussed at all, but it does use some advanced number theory that we can skip, but you should be able to read on in your own time. So this is one suggested thing that we can talk about in the last chapter if you're interested. Um, Yeah, it's one. It would be like a glimpse to very advanced subjects, which I don't think even 315 covers, unless I don't know. This is very specific, so you can think about if you're interested in this. I will of course suggest other topics as well, but this is one way to connect things with elementary number theory, right? The fact that modular arithmetic doesn't help at all is interesting enough to be um, talked about this. Okay, so there's a good video in the chat I'm reading. There's a good video on p-adic numbers, which were ultimately used to prove the theorem. You mean Fermat's last theorem or Schur's theorem? I'm guessing Fermat's last theorem, right? Yeah, of course. Yeah. I do know people in the math department who understand this proof better than I do, but I don't think I know anyone who can who knows every single detail about this proof. It's quite lengthy. I think the main paper is like 120 pages, which doesn't sound like a lot, but of course it covers a lot of context. Anyway, this would be something that you would have to study over several years, maybe even a very specialized seminar just about this. Like I said, I have no idea why Fermat's theorem is true. There's some funny consequences of it though. Anyway, so let's continue with the next topic, which will be about, okay, we saw some applications of modular arithmetic. So how do we solve modular arithmetic problems then? We know how to use it, we know what it is and how it works. So let's maybe try doing some more things, right? So solving congruences is the next subject. Everything we've done so far, in my opinion, has been elementary, and that's not a way of saying that it is easy or not worth doing or something. It just means that we haven't really used any incredibly novel idea to prove anything. I mean, the definition of congruences might be novel enough for a lot of people seeing this for the first time. But the first non-trivial theorem about number theory will be Fermat's little theorem. That is one that actually takes some new idea, some insightful idea about numbers that you cannot just come up with by expanding out definitions. So before we do that, let me tell you the basics. So how do you do this, right? What are the very basics? So I mentioned in the past that the reason we're doing all these quotients and defining bigger and bigger structures is to solve equations. So the first equation that we cannot solve in the integers general is how do we solve? Something of the form ax equals b. Of course, I'm going to add this symbol to denote that this is being congruence. Let me pause the recording real quick.